Welcome back to Chem 4300. In this video, we're going to continue Chapter 16 on the quantum particle moving in 3 dimensions. Now, as we continue exploring the consequences of motion in more than one dimension, we finally come to a very important topic in quantum mechanics, the quantum theory of angular momentum. So let's see how that's treated. Now, if you remember from classical physics that the angular momentum is the cross product of the position vector and the linear momentum vector. So L, angular momentum, is R cross P. Now, something you have to keep in mind when you're working with angular momentum, whether it's in classical physics or in quantum physics, is that angular momentum depends on how you define the origin. So different origin choices will lead to different angular momentum vectors. So keep that in mind and be careful with whatever problem you're working on that you define your origin in a consistent manner. Now, with this picture here, we have the classical L equals R cross P. We can convert this into a quantum set of operators by just putting hats on them. So we have L hat vector is equal to R hat vector cross P hat vector. Now, for wave functions in the position basis, our momentum operator will be given by minus I h bar times the gradient operator. So expanding this out, then the angular momentum vector operator is minus I r vector operator cross the gradient operator. So now we have to evaluate this cross product. So if you remember, when we evaluate these cross products, we do this with a determinant. And so R cross P is this 3 by 3 determinant, which is Ex, Ey, and Ez, which are the unit vectors. And then we have the operators, X, Y, and Z, and then Px, Py, and Pz. Now, something you have to remember is that operators do not necessarily commute. So X times Py will not be the same as Py times X. So we have to evaluate this determinant, being very careful that we expand it correctly and consistently, because in quantum mechanics, this is going to matter because of the non-commutation of these quantities here. This is not a problem in classical physics, but in quantum mechanics, we have to be careful expanding this determinant. So first, I'm going to expand it out with the unit vectors, which are not operators. So I now have Ex times this 2 by 2 minus Ey times this 2 by 2 plus Ez times this 2 by 2. And now I have to evaluate these 2 by 2 determinants, which are full of operators. So here's how we're going to do it. Y times Pz minus Z times Py. And that's going to be the Lx component. Similarly here, it's going to be for Ly, X times Pz minus Z times Px. And then don't forget there's a negative sign out here that comes with this component. And then for the Z component, X times Py minus Y times Px. So when I write those out, these are the angular momentum components, operator components for Lx, Ly, and Lz in terms of position and linear momentum. Okay, so now we're going to take these and see what we can learn about their eigenvalues and eigenstates. So here are our operators written in terms of position and linear momenta. And one thing you have to keep in mind also is that the linear momenta commute. We didn't actually show this in the first part of this chapter's video, but you can easily derive this from those definitions of Px, Py, and Pz and see that they all commute with each other. But when you look at Ly, Lx, X, Ly, and Lz, you find, well, they actually do not commute with each other. And so this is not obvious. You have to prove this. So you'll have to take these definitions, plug them into these commutators, and evaluate them out in terms of the commutators for X, Y, Z, Px, Py, and Pz, and redefine them, and you'll get this result here. So this is a good homework problem to prove these guys. Now, if you want to remember these, they're always times I h bar times the other component. So here it's X, Y, and then Z. And here it's Y, Z, and X, and then Z, X, and Y, and they're all times I h bar. Now, the order is important, of course, because if you change the order in the commutator, you change the sign. So to make sure you get them straight, remember this rule here, that there's always a cyclic permutation of the subscript. So in other words, you go from x to y to z to x to y to z, and so on. So x to y to z, and then you see we start here y to z, and then back to x, and then you have z, and then back to x to y, and then you continue. So that sort of rule will help you remember how to write those out by heart if you need to. One thing that we know from commutators for operators that do not commute is that there is an underlying uncertainty principle associated with those operators. So we knew that x and p don't commute, and there was the uncertainty principle, which we know from, which is Heisenberg's uncertainty principle. Well, here from these commutators, we can get this uncertainty, which, so for example here, Lx and Ly do not commute, and they give you I h bar times Lz, and so the corresponding uncertainty principle is that the uncertainty in Lx times the uncertainty in Ly is greater than or equal to h bar over the absolute value of the expectation value of Lz, and similar ones for these other two commutators. Okay. So that means that you can see already that we cannot simultaneously know x, y, and z operators, but we'll see more of this here. So the total angular momentum operator, written in terms of those components, will be L squared is equal to Lx squared plus Ly squared plus Lz squared. And what we find is that this total angular momentum operator will commute with each one of the individual components. So L squared commutes with Lx, it also commutes with Ly, and it also commutes with Lz. And it also commutes with the vector L operator. But that doesn't mean that Lx, Ly, and Lz commute with each other. We just saw that that's not true. But L squared does commute with all three of them. Okay? So what this means is that whatever the eigenstates are for L squared, they can't be simultaneously the eigenstates for Lx, Ly, and Lz. So it can be the eigenstates of L squared and Lx. So these two guys can share an eigenstate, or L squared and Ly can share an eigenstate, or L squared and Lz can share an eigenstate, but all of these operators can't share the same eigenstate because x, y, and z do not commute. So we know that we cannot simultaneously know all three components of the angular momentum vector in quantum mechanics. And so this is going to be an issue. It's going to make things really interesting. And like if you're just adding vectors, for example, if you're adding two vectors in classical physics, it's pretty straightforward. You add the x components, the y components, and the z components. If we try to add angular momentum vectors, we find that we can't do that because we can't simultaneously know all three components of the two vectors in order to add them. So that's going to have serious consequences as we go forward. So we can only know the length and one of the components. That's all we can know because of these commutation rules. We can pick one, but we can know x, y, or z and L squared, but we can't know any more than one component and the length. So the convention actually is to say that we're going to work with the eigenstates of L squared and Lz. Now, you could easily work with Lx, Ly, and L squared. It doesn't really matter, but our convention is that we're going to say that the eigenstates we are working with are L squared and Lz, and assume that Lx and Ly are the non-commuting observables that don't share these eigenstates. Okay. Now we come to working out what are the eigenvalues of these angular momentum operators. And so this one is going to be a little tricky, but we'll go slow here so that you can follow the arguments. So we're going to work this out without actually looking at the wave functions for these operators. So we're going to have a generic wave function we'll call psi, and we want to work out that L squared operating on psi is going to give us back some yet to be determined eigenvalue, which we'll call lambda, and Lz operating on the wave function is going to give us back some also yet to be determined eigenvalue we'll call mu. Now, in order to do this without getting into the details of the wave function, we're going to introduce these two operators called the raising and lowering operators, which you may remember from the chapter on the harmonic oscillator. So we're going to do it in a slightly different context here, and we're going to define two operators, which are L plus and L minus, which are defined as Lx plus ILy for L plus, and Lx minus ILy for L minus. And these raising and lowering operators are going to help us in our derivation here. So first we need to figure out what those operators actually do. So if you imagine the sort of go back to look at the derivation we did with the harmonic oscillator with the raising and lowering operators, or the creation or annihilation operators, you'll see very similar derivation here. So you imagine if you take the L plus operator and you operate on some wave function, you're going to get back some other wave function. We haven't said anything special here. We just know that it's going to do something and it's going to give us back some other wave function here. So now we want to know is what is the effect of L plus on this other wave function? Well, let's take that wave function which we've transformed and let's ask for its LZ, this eigenvalue. So we'll operate LZ onto that new wave function, which then gives us, when we multiply out back to the original wave function, the product of LZ, L plus times the wave function, or in the proper order, we first apply L plus to the wave function and then we apply LZ to the wave function. Now, I want to figure out what happens when we do this, but what I'm going to do is a little trick here. It's kind of a little mathematical sleight of hand. I'm going to take this result here, that LZ times our transformed wave function, which is equal to this. I'm going to take that equation there and I'm going to add 0 to it. All right, this is just a trick, but it will be very useful here. I'm going to add to it minus L plus LZ times the wave function plus L plus LZ times the wave function. And what this does for me is it allows me to rearrange this a bit so that I now have LZ L plus minus L plus LZ times the wave function plus L plus LZ times the wave function. And this part here becomes this commutator LZ L plus. And using the commutation rules that we saw on the previous slide and our definitions for L plus and L minus, you can work out that that commutator is equal to H bar times L plus. So by adding 0 and then rearranging, I've created a term here which I can simplify down with the commutation rule here to H bar L plus. And so now this result becomes H bar L plus times the original wave function plus L plus times LZ times the wave function. But if LZ operates on the wave function, I get back my yet to be determined eigenvalue. Okay, so I did a little trick here that allowed me to sort of get the LZ off to the other side. So here's my LZ, it's on this side. By adding in 0, rearranging this guy, I was able to put LZ inside over here, which I can then directly evaluate and leave me with L plus times that unknown eigenvalue times the wave function. Okay, if you're with me so far, let's go to the next step then. If I take that result, which is right here, then I see that H bar times L plus on the wave function plus H bar times this eigenvalue on the wave function. I can pull this eigenvalue past the operator because it's just a number, and I can bring it over here with the H bar. So I now have H bar plus the unknown eigenvalue times L plus on the original function. Okay, what did I do? Well, I learned that L plus increases the eigenvalue of psi by 1 unit of H bar. Okay, so in other words, if I apply LZ on my wave function, I get back my unknown eigenvalue times the wave function. If I apply L plus on that wave function, I'll get some new wave function. And when I apply LZ on that new wave function, I get back my unknown eigenvalue raised by H bar times the new wave function. So the job of L plus is to take a wave function and increase it to the wave function that has a eigenvalue that's h bar higher than the one that was operated on. Okay? That's why it's called the raising operator. It operates on a wave function, takes it to the one with higher angular momentum. Now, one thing you might not have noticed yet, but the h bar, which is Planck's constant divided by 2 pi, has units of angular momentum. So what we're seeing is that this is one quantum of angular momentum it's been raised up by the operation of L plus here. So L plus raises this wave function to the next wave function, which has one higher quanta of angular momentum associated with it. So if we did the same thing with L minus, we can prove that L minus will reduce the wave function to a state that has one less h bar in angular momentum. So this L plus and L minus are called the raising and lowering operators for what I hope now are obvious reasons. And so when we apply L squared, we get back still some unknown value we have to determine, and we know that LZ will give us back some unknown value. So, and we know that h bar is this unit of angular momentum, so we still have to determine these two constants, but we're going to use now this behavior of L plus and L minus to help us figure out what lambda and mu are. So if I apply L plus, I can't apply L plus to an eigenstate of LZ and get a value back that's bigger than the length of the total angular momentum vector. Right? If you think about it, a vector quantity, so the total angular momentum has an x, y, and z components, right? So the length of the vector is the maximum you can have along x, y, or z, assuming it's perfectly aligned along each of those axes. So if I apply L plus to a wave function, I can't take the LZ eigenstate and create an LZ eigenstate with a angular momentum value that's bigger than the total angular momentum value. So that cannot happen. So no single component can exceed the total length of the vector, right? So if I take L plus and I take it and I apply it to what I call psi max. Psi max is the eigenstate with the highest possible eigenvalue that it can have, then it has to give me 0. And what I'm going to say is that psi max, if I operate with LZ, I'm going to get some unknown number times h bar, which is in units of angular momentum, times the original wave function. So what I've done is I've taken my mu, and I'm saying that mu is equal to L times h bar, because I know it's going to be in units of h bar, or units of angular momentum. And so I want to figure out what this undetermined multiplier is, which is L. And of course, I know that if L squared acts on the wave function, I get back this lambda, and that doesn't really matter whether it's the maximum or the minimum or any value in between. It always returns the total length of the angular momentum. And that's what I want to determine now. So I want to determine this lambda, and I want to determine this L, which is essentially L is equal to mu is equal to L times h bar. So here's what I have of my constraints. I have, and I'm going to start by applying L squared to the psi max, and I get Lx squared plus Ly squared plus Lz squared, and that's going to give me back lambda times psi max. Now, here's where it gets tricky. I'm going to use an identity which says that Lx squared plus Ly squared is equal to L minus times L plus plus I h bar times Lz. It's also equally equal to L plus times L minus minus h bar times Lz. Now, where did I get this? Well, you can prove this. I can work through a quick proof here, and you can try this yourself. If I take Lx squared plus Ly squared, and I write it out in terms of raising and lowering operators, and that's just L plus plus L minus over 2 twice, since it's Lx squared. And then for Ly, it's L plus minus L minus over 2I twice. And when you multiply all of that out, you get some complicated expression here, which you can keep simplifying, and it will end up looking like this here. Now, what I'm going to do is I'm going to use the fact that the commutator of L plus and L minus, which is L plus, L minus, L minus, L plus, that commutator works out to be 2h bar LZ. Again, you can prove this given everything we've learned so far. So I can rearrange this and say that L plus L minus is, oops, that's a stray there, sorry about that, is equal to 2h bar L plus L minus L plus. So I can replace this over here with this term, and when I finish rearranging this, I'll get this expression here, which is exactly what I wanted to prove in the first place. Okay, now you can do the same thing with the other result. So just check through this to make sure, but you can see there's a lot of things you can do when you have all these commutator relationships defined out. So that allows me to make this definition here, and I'm going to take this and replace these two terms, and when I do that, I get this expression, and then when I evaluate these, you see that LZ squared on phi max is going to give me L squared h bar squared. H bar LZ on phi psi max is going to give me L times h bar squared. Okay. And then when I do L plus L minus on psi max, well, L plus operates on psi max and it gives me 0, so I have nothing. So when I multiply this out, I get L times L plus 1 times h bar squared times psi max. So that has got to be equal to lambda times psi max. So now I've identified the relationship between the eigenvalue of LZ and the eigenvalue of L squared. So now I see that lambda is equal to this expression here. Oops, sorry. And let's do the same for L minus. So if I take L minus here, I have the same kind of relationship, except this time I'm going to say LZ on L min is, I'm going to call that L prime. Let's not make any assumptions about what this is going to come out to be. We still need to figure out what this L prime is. So now I'm going to do the same approach, L squared on psi min, the same thing here, and I'm going to use that definition that I had earlier to replace that. And so this is replaced by that. I evaluate it out, and I get now LZ on psi min gives me L prime h bar squared, and then minus h bar LZ on psi min gives me minus L prime h bar squared, and of course L minus on the min has to give me 0 and leaves it like that. And so when I write this out, I get L prime times L prime minus 1 h bar squared times psi min. And that's, again, has to be equal to lambda times psi min. So that means that lambda is equal to L prime times L prime minus 1. And we just learned in the previous slide that it's equal to L times L plus 1 times h bar. And so this can't be, this can only be true if we have L prime is equal to minus L. So that means that we've now found that our eigenvalues of L squared is L times L plus 1 times h bar squared. And for LZ, we find that it can go from minus L times h bar for the min to plus L h bar for the max, and it has to increase in steps of h bar. Okay, that was a pretty long proof, but what's nice about this is we didn't even use the form of the wave function here. We derived it entirely from just using this L plus and L minus approach. So the summary here, we've gotten to the boxed equations. The summary here is that L squared times the wave function operating on the wave function gives you L times L plus 1 h bar squared, and LZ operating on the wave function gives you m times h bar times the wave function, where m are values of minus L plus 1, all the way through to L minus 1 to L, which is a behavior that you're probably already familiar with. So if there are n steps between m equals minus L and m equals L, then that means that L has to be equal to minus L plus n, which gives us possible L values of n over 2. So that means that for L, we can have integer values of 0, so n can be equal to 0, it can be equal to 1, n can be equal to 2, and so we end up with 0, 1/2, 1, 3/2, and so on for possible values for this L quantum number. Now, one thing you might have noticed here is that the maximum eigenvalue for Lz is smaller than the total angular momentum. This is the total angular momentum squared, so if I take the square root, I find that L times h bar is always going to be smaller than the total angular momentum. So that means that L, the Lz component, can never lie directly, the total angular momentum vector can never lie directly on the z-axis. There has to be some uncertainty because of, if we had it entirely along the z-axis, then Lx and Ly would be 0, and that wouldn't be allowed. So the maximum value we can find for Lz is always some value that's less than the length of the vector. All right. Okay, so now that comes to the end of this video, and in the next video we'll look at how we derive the wave functions, the eigenstates for these operators.